Hello. So this recorded lecture is on the topic of individual claim reserving. It's the last lecture in my course, Deep Learning for Actuaries. So, um, of course, if you're in this class, you'll know that, but I'm considering putting this recording more publicly available online. So if you're a stranger coming across this, some of the topics I present today will require the background knowledge of the previous lectures in this course. So the lecture, the main topic is, as I said, individual claim reserving with neural networks. The plan is to define this because I don't assume that you've seen this problem before. Talk a bit of detail about what an individual claim looks like, what kind of data we have in the reserving situation. Very briefly compare it to what we have a more traditional way of doing reserving, like the chain ladder, but this is very de-emphasized. And then get into some of the choices that we have when we are turning this into a machine learning prediction problem at the individual level. And there are a few different choices we can make. It's not like there's one correct way to do this task. At the end, I'll zoom in. I've got some synthetic data set, which is synthetic claims that are designed to be very realistic. So we'll try to fit them and compare a few of the models, talk about the metrics that are involved because they're not standard metrics, and then wrap up. Okay, what's the problem that we have? In individual claim reserving, an insurance claim has already happened, and the policyholder has told their insurer, okay, this happened, I need to get paid for it, and maybe the notification's already happened, a year ago, and the claim is still dragging on. The insurer wants to know how much they'll have to pay in the future from the current time all the way until the end of this claim. So here, this little diagram is just a bunch of fake numbers to show you the life of a claim, basically. So the accident happens, there's some delay until the policyholder notifies the insurance company, and then what I've got here as process is a sequence of payments happen from the insurer out to the policyholder all the way up until the claim is just finalized. Everything that needs to be paid has been paid, and this is called the claim being finalized. These are just small numbers here, just so that they fit on a slide. They're all synthetic, but this is the general outline of the context we're in. Now, the thing that matters that we want to be able to predict is this ultimate claim size. So for a specific claim indexed by K, well, the ultimate claim size is the sum of all the payments that went from the insurer to the policyholder over the entire lifetime of the claim. So what was ultimately paid to the policyholder. Because the payments happen in a stream, they don't all happen in one lump sum. These are called incremental payments, what I'm calling PK, T, or sometimes partial payments. So ultimate claim size is the sum of all these incrementals. Now, there's lots of terminology in this field, so I hope I'll go through this first part of it slowly so we don't overwhelm you with all the terminology. And there's also lots of fiddly little parts with individual claim reserving data, which make it a bit of a pain to deal with. Now, here's one straight away. Sometimes, for today's lecture, we'll just take the simple case that payments are all positive, and that might sound silly to say, but there are these, in reality, these kind of negative payments called recoveries, where the insurance company actually makes back some money due to complicated reasons. But these are normally rare and in size they're quite small compared to the real payments, so we'll be ignoring them for today. But in reality, this does happen. Okay, now the next main topic, main idea I want to drill into you at the beginning here is this idea of the outstanding claim amount. Now, this is linked to the ultimate claim size, but it's relative to when we are in time. So let's say V is a specific date, which we want to call, I'll call this the valuation date through today's lecture. And we've seen the history of the claim up to that time. So I'll call that H, K, V, which is the history, all the information about the claim K up to time V, valuation date V. And that, in particular, that includes all the past payments that have been made to the policyholder. Now, the outstanding is the future unpaid amount for that claim. I'm calling it here big O of K brackets V. Basically, that is how many payments in the future remain to be given, sent to the policyholder. So for all time after the current time V, the sum of all those payments, everything that's left to go. So if the claim is partway through its progression, so it's been notified but it hasn't been finalized yet, and the valuation date is sometime in between there, then we have that the ultimate claim size is the sum of all the claims up till the valuation time V. That's the cumulative payments, or the cumulative paid to date, plus the outstanding amount. So in words, ultimate is how much have we paid in the past, plus how much will we pay in the future. So this is a key, it's quite simple here, but we're going to be layering on lots of different concepts. So this is a key one to keep in mind. Ultimate is cumulative payments in the past, which we have observed at time T. That's something we know. And then the outstanding is something we don't know. At time V, this is the key thing that needs to be predicted. So this is one claim, but insurers have many policyholders in a portfolio, and for a whole portfolio of claims at a specific time, valuation date V, one thing that's also very important, that's actually more important, is they want to know how much in total is outstanding. How much will they have to pay for all the claims that have already been notified in the future? So here I'm using some new notation, calligraphic O for the set of all claims that are open at that time. So summing over all the claims that are still in progress, haven't been finalized yet at the time V. For each of those claims, how much will we need to pay in the future? So that's what I'm calling TOV, the total outstanding. So this is an interesting, important quantity. It doesn't actually capture everything though, because the insurance company still has this other stream of payments they need to make for the claims that have actually happened. So there has been an accident, but the policyholder hasn't yet told the insurance company about it. So those are still claims that aren't captured by this quantity here. We're just zooming in on the claims that have been notified and that we know are ongoing. Then TOV is going to be an underestimate of all the actual payments that need to be made. So to draw it visually, I'm going to draw plots like this a few times in the lecture. And the way that you read them is that time is on the x-axis from going left to right. And each of these lines represents a different claim. So claim 1 is this first horizontal line, and then claim 2, 3, and so on. Now, here I'll draw the crosses to mean a payment will happen. These small crosses. The big cross at the end here means the claim is finalized, it's finished, and the circle at the start means it's been the beginning of the claim. So either the claim has actually occurred, so the accident date, or the claim has been notified to the insurance company, depending on which slide I'm on. So here the claim 1 started early and then has already been finalized before our valuation date V. So actually we don't care about that claim, it's already wrapped up. Claim 2 doesn't matter as well, it's in the past. claims 3 and 5 and 6 are ones that in this illustration we care about, because they haven't yet been finalized. They'll be finalized in the future relative to if today were time t10. So these claims have been notified. They've had a couple of payments made to them, but here in pink is the part that we really want to be predicting. We want to be able to predict the sum of all the payments in the future up until finalization. So that's the outstanding for this claim, outstanding for claim 3, the outstanding for claim 5 and 7. So we add up the payments there. Yes, and then here is that that caveat that I just mentioned. Here, let's pretend that this last one is an accident has happened, just at time 8.5 or something, but the notification has been delayed by the policyholder until sometime in the future. So this claim is still something we'll have to pay out, but we don't know about it yet. So we can't really deal with that. Well, at least I won't go into the methods needed to deal with that today. That's a separate thing. Okay, this is a different task to the general insurance pricing prediction, which we've done many times in the course. Estimate the frequency, estimate the severity of the claims. Now, that's because pricing is thinking about claims that haven't happened yet. I think about this policyholder. I try to guess what type of claims might they generate in the future. These are all hypothetical, and we only have some covariates about the policyholder themselves or the policy. Reserving is a bit different. We've got all that information, but we also have the fact that something really did happen. We have a claim, and we already have the some information about the claim. If we're sort of in progress already, we know how much has been paid up until now, and this other thing called case estimates, which I'll explain shortly. And so we have more information than just the sort of static covariates about the policyholder. And this means that for machine learning setup is sort of there's pros and cons, right? We always want more data, more valuable predictive data. But for us, because these features are time varying, it's a little complicated just to keep track of everything. So that's why this whole lecture is a lot about keeping track of the information that we have and sensibly pre-processing it. Okay, so that's the introduction. Let's move on to, mainly getting to the case estimates that I mentioned and bringing together all these time varying covariates. So from the perspective of one individual claim, a few things are the most important. So we have when did it happen, the accident, when did the insurer find out about it, the notification date, and then when did this whole thing get wrapped up, the finalization date. Now, later on, I'll have a slide specifically about this, but we don't, for a lot of the methods, we don't really care about the individual day of the week and of these things happening. Most data we're going to group into summarized by each quarter. So here there's where I've written the main notation I'll be using is AK, NK, and FK for the accident quarter, for the kth claim, notification quarter, and finalization quarter. As I said before, this calligraphic O, I'm using that to denote all the claims that have not yet finalized at the time V. And here's one of those little fiddly things that happen in real data. That is, sometimes a claim finalizes, but it finalizes too early, and then it gets reopened again, and then more payments get made and gets finalized. Maybe that happens even multiple times. Yeah, we're just going to ignore that, but that again, it does happen in real data. So what are the main sort of new covariates that we have, which is the series of incremental payments. Here, these are just made up numbers. Of course, they're all way too small, but just to fit on the screen. And from the policyholder's perspective, they would have this day-by-day information. So maybe this is their bank account they have, on this specific date, the first payment from the insurer came in, and all the series of payments came in until the end, and then we finalize. Now that's from the policyholder's point of view, but from the on top of that, the insurer has sort of more information. They have this team of experts called case assessors or case estimators, and their job is to actually look at the claim, all the details of the accident and the everything to do with how it needs to be repaid. And they will, at different times, come up with a new estimate for what needs to be paid out in the future. So this case estimate here, CKV, that is, here I'm writing this notation to denote a case estimate, which is a prediction from, not from a machine learning company, machine learning algorithm, but from a person using their expert judgment. They look at all the information that our models are going to look at, and then they come up with a number for how much is remaining to be paid on this claim. So it's a guess of the outstanding. Now, this is useful because for our algorithm too, because if our algorithms can read this in, this is valuable because these are known at time V. When the assessment's been made, that we have access to that case estimate, which is roughly, we hope, approximately equal to the true outstanding amount on that claim at time V. But the thing here is, this is what we're trying to predict, and it's not knowable until in the future when the claim finalizes. Only in retrospect do we know what the outstanding was back at time V. We don't really know the ultimate until the claim is finished. Now, this is beneficial for a couple of cases. We can use these case estimates as a potentially very strong predictor, that covariate that feeds into our models, because it's trying to do what we're trying to do. It's trying to predict how this claim will develop in the future. And another thing we could do is we could treat it as a benchmark. We can say, our models, do they beat what the case estimates are or not? Now, these happen at different times. So, for example, there might be different dates of payments, and the case estimator might open up a case, open up a claim, see, maybe a very large payment happened, or they looked at it and they saw, oh no, this claim is a spinal injury claim. That's going to be a big one. I'm going to up my estimate from what it was before to a larger number, basically. So these case estimates happen at irregular times, and we've got these two streams of very highly predictive time-varying time series, basically covariates. So I'm going to plot them to really illustrate it. Here is a synthetic claim where and I'm calling it from the policyholder's perspective, because if I have a claim, I tell my insurance company that I want you to pay me back for this thing. The main thing I care about is how much money they're going to give me, and maybe when I'm going to see that money. So this is why all these plots are the ones that are going up. See, the green one here is the cumulative payments over time. So after I've notified the insurance company, I've had to wait 2 quarters to get the first payment, which was $10,000 roughly, and then a sequence of small payments up until the end, until we have the finalization sometime around 8 quarters later. Now, the sum of all those payments, all the way to the end of the claim, that is this dashed line, which is the ultimate. That's what me, as the policyholder, that's what I want to know. Well, what's this going to be? Now in purple here is a version of the case estimates that I explained a moment ago, which is designed to guess the ultimate. So here, this purple line is a sequence where the case estimator has opened up the claim. When the claim was opened, they came up with a guess based on the initial information. Oh, this looks like a claim that'll be $30,000. And then later on, a couple of quarters later, they got some new information, and then they did a large revision. They said, "Oh wow, this is actually a much bigger claim. We guess 45,000 now." And later on, again, they do another revision and revise their estimate of the ultimate to eventually these things will match up in the end. So those are all the versions of of tracking all these numbers that are going up. But from the insurance company's point of view, they actually don't care really about that. They only care about, I've already paid the things that have happened in the past. I only care about what's happening in the future. So from the insurer's perspective, really what they want to know is the outstanding. So from the beginning, when the claim begins, the outstanding is exactly the same as the ultimate, because we haven't paid the policyholder anything yet. So we started the ultimate, and as payments happen, the amount left to pay on this claim will drop, eventually to zero by the time of finalization. And the case estimate here is I've drawn in, what do you call that color, browny orange. It's just a flipped version of this purple one. So here the incurred is, I've written down the bottom, is the version of the case estimates which is trying to predict the ultimate, whereas what I'm just going to call the case estimate without any, this is sometimes called the OCL. What I'm going to call the case estimate is just this human expert's guess of how much is remaining on the claim. So CKV. So the terminology here is like a bit blurry, so I'll try to keep it one version consistent in the lecture here, even though I know in practice some these get tossed around with different meanings. Okay, now let's move on. That was one claim over time, and we'll jump into all the things needed to handle all that information. But before that, let's just do the simplest one first, which is the aggregate reserving benchmark. To explain that, I'll just highlight the 3 different levels of the claim data granularity that I'm going to be talking about today. And this will come up in next week's lecture as well. So up till now, I've been talking sort of at the ideal level, which is every single transaction at each specific date. Now, maybe the insured bank statements include all those low-level details, but the actuaries rarely get such low-level details. For them, because they're looking at our portfolio, they are typically working on claims that have been already summarized to the level of what happened in this quarter, or even if they're lucky, maybe what happened in this month. Now, this is where we'll be operating most of the individual claim prediction later in today's lecture. But this is still, each claim is separated. The highest, the least granular version of the data is to summarize all the claims, all the payments made out to anybody within a quarter gets added up together. So that's actually what I'll be showing you now is the simple benchmark, which is not individual claim prediction at all. It's actually this aggregate reserving method called chain ladder. So this is I'm not going to emphasize chain ladder a lot because it's not the point of today's lecture, and I don't know much about it. So take everything I say about chain ladder with a grain of salt, but I can kind of remind you. You should have seen this in previous courses, so you know more than me. Yeah, but The idea is that you create a triangle of this portfolio level information where you've got all the claims you've in the past that you've separated by the year, or I'll put year here, but it could be quarter or month. But let's say by the year of the accident, you organize that by each row. Each column is how the year it develops. So here, this number, let's say this is in, I don't know, hundreds of thousands of dollars or something. That this is representing the fact that all the people in our portfolio who had an accident in 2021, within that same year, we paid out $100,000 to all of them. Now, not all claims would have settled within the first year, though, so claims will drag on. The claims that dragged on to the second year will, if this is the cumulative version of this triangle, which means that this number here, 150, represents how much we paid to all the accidents that happened in 2021. How much did we pay to those policyholders within the first 2 years? So within 2021 and 2022. So this is bigger than the previous one, 150. And then finally, within the first 3 years that they developed, up to 165. And chain ladder is called a triangle because at some point we don't know, right? We don't know if this is, say, 2026 is the last row. We don't know how many will be paid in development year 2 because that's in the future. That's the job of reserving, filling in the triangle. So chain ladder is my understanding is it's quite a simple kind of a set of assumptions. They look at, say, here we see like how much does this cumulative amount pay jump when we go from development 2 to development year 3. So in this case, we only have one observation where we have the full triangle, well, the full part of the triangle representing 2 to 3. So we would take this ratio here, 165 divided by 150, and then use that fraction to multiply by 180 to come up with an estimate for this number here. And then also to multiply by this number when we come up with an estimate to fill it in here. And whereas I think I've got it in the next slide. Yeah. Whereas say from year 1 to year 2, we've got two observations going from development year 1 to development year 2. So we sort of average them together to come up with a new factor, and that 1.5 is applied here to increase 140 to 210 and so on. So once you've filled in all the estimates, then you can basically figure out how much is left. How much do we need to keep in reserve, because what's left from this triangle, what's the total outstanding for the portfolio. Now this is something you can do in a spreadsheet. It doesn't require a lot of well, it can be done. There can be lots of subtleties. I shouldn't diminish it. There can be lots of subtleties, but compared to the individual claim reserving, I think overall it's safe to say it's a bit simpler than the individual level, because we throw away lots of information. The triangle, we've already thrown away who exactly was injured in the claims, like anything to do with the claim severity, the ages, or something like that. We don't know. We don't know, for example, any of the progress of the claims. We don't have the case estimates either at this level. Now, this is why it's so simple to apply, because we're using less information. Now, and why would we go from such a simple method, the aggregate level, down to what you'll appreciate is more complicated, the individual level? Well, I'm going to punt that to next week. I have a great guest lecturer Professor Greg Taylor, who is the world expert in all of these things. So in his guest lectures focusing on this exact topic, so I'm not going to really go into it here. But that's, of course, there's always pros and cons to both methods. We're going to look at the individual level for two reasons. One is that it's much more promising for neural networks and for machine learning methods in general. There's more data, richer structure. Secondly, I actually have some experience with this specifically. So I completed some contract research with one of the state, I'll be a bit vague, one of the state governments in Australia. So we had access to all the motor claims that happened in that state in Australia for the last couple of decades, and we were tasked to use neural networks to predict the reserve at the individual level. So some later in the lecture, I'll talk about sort of generic choices one could make when doing this task, and I'll probably also hint at some of the choices we did make for this specific work to tell you what we did, why we did it. Well, I didn't mean for this to lead in so perfectly, but that's what we'll do next. We have a few choices that we need to make when we're doing the modeling, and I just wanted to set them out up front, the high level ones, before we get into the low level details. For the individual claim prediction, at a high level, we need to decide what are we feeding into the model, what do we expect to get out from it. So I'll focus on the outputs first. And this task is like quite a bit challenging compared to many neural network, sort of standard neural network tasks, is that we're always making predictions from the perspective of this valuation quarter V. So that complicates things as well. Now, the individual claim model, in general, of course, the input would be, we want to have some kind of covariate input X for claim K at valuation date V, which summarizes the claim's history up to V. So that's what we want as input at a generic high level. But the output, we have two main questions, two choices. One is, do we want to predict the ultimate claim size, or do we want to predict the outstanding value? So remember, these are, you can work out one from the other relatively easily, right? Because we've got, I can't find myself in my own slides. Yes, okay. So the ultimate is simply how much have we paid cumulative payments to date plus the outstanding. So we can always convert one to the other if we need to, right? It's not but there are some subtleties in which one you choose to model. So are we trying to predict the ultimate or the outstanding? And the other one, which I'm not going to go a lot into today, which is, are we doing sort of point-wise forecast, or are we trying to predict a whole distribution for each claim for the target variable? So as I said, I'll touch on this a little bit, but this is not the main focus today. Now, focusing on what's the difference really between predicting the ultimate or the outstanding. So here, let's say we're looking at one claim at a specific valuation date V. How much has been paid to date, this cumulative payments, are put as a vertical dashed line here. So let's say about $60,000 have been paid out on this claim up till now. If you had a model that is predicting the ultimate, then it depends how you set it up, of course, but if you're predicting the ultimate, those kind of models typically can spit out, predictions between 0, up to infinity. So they're just constrained to be positive. And here I've drawn densities because in that contract work that I mentioned, we did actually do distributional forecasts here. So in this case, let's pretend we're predicting a distribution over the ultimate. Then this green curve could be one prediction we make for the ultimate, but is a little unsatisfying in some sense, because the model here is adding some probability. If you integrated this section of the curve here, if you integrated that, you would get a probability which the claim is saying, sorry, the model is saying, this is the probability that your ultimate is going to be less than how much has been paid up till now. Now, it's not that this is not the completely nonsense artifact of the model, because remember, in reality, there are those weird recoveries. So it is possible that you pay, and then you have a recovery, which actually means that you have a negative payment. But those, as I said, are rare and small. So if we're ignoring them, if we're pretending they can't occur, then this becomes a clear error, that we allow for the predictions to be less than the payments up till now. The other side is if we predict the outstanding, and we so ultimate always greater than 0, outstanding always greater than 0, it's a bit easier to avoid that problem. So if we're predicting just the outstanding, which here I'm drawing as this purple curve, it's sort of by definition not letting you predict less than the payments made till date, because they're saying, this is the payments made to date, is this dash curve. My model is always going to give me a positive amount, which is how much is left. So this is one of the reasons why we'll be sticking to the outstanding as the target variable in today's lecture. Another thing is, how do we deal with the fact that a claim goes for a very long time? We need to convert this into one row of input in a training or validation or test set. So what I'm calling claim snapshots is a high-level summary of how we do it. And this is something this terminology, I made this up, so you won't be able to Google it. But the logic is that a claim is open from notification quarter to the next quarter, all the way up to when it's finalized at the finalization quarter. And we could view it, or do the valuation V for each one of those quarters. And that's what we do when we create a data set, so a training data set. We do grab a claim that eventually finalizes. We look at it retrospectively for each quarter that it was open, and we turn that into a training example. So basically, we watch this claim K all the way until it finalizes, so we know what the ultimate value was. We can work backwards to retrospectively figure out what the outstanding value was at each of the different quarters, and then we turn each one of these quarters into a new row of input. So if this is the one claim here on the left, turns into many rows of input in the data. So the first notification, NK, all the information that we know about the claim up until the end of that notification quarter becomes summarized in XK, NK here. So that's our inputs for our model, and our target we try to predict is the outstanding that's left by the end of the notification quarter. And then we move, so that's the V is here. Then we move the valuation quarter along and make a new summary. We move forward in time. We say, okay, what was known one quarter later? Summarize that information. What was the outstanding at that time? We calculate that as a new target. So one claim now turns into a whole sequence of these claim snapshots, which are different individual rows of input to the models. Now, one kind of strange thing about this actually is that, before I get to that, I'll say we move the valuation perspective from notification all the way up to finalization -1. Now, the reason for that is if we actually look at the claim from finalization quarter, then the claim's already finished. There's actually nothing to predict, so it's not interesting to build a model on that. So we throw that away. And one consequence of that is that if you have these claims that notify and finalize all within 1 quarter, then this kind of method will actually they'll just disappear completely from our data set because they won't have any claim snapshots made about them. But anyway, you could say these are probably very small, simple claims that don't make a big deal at the end of the day, but maybe this should be adjusted for. Okay, now let's step into, we've made some high-level choices. How do we really wrangle all of this strange data into something the neural network can handle? So I've got some kind of interactive graphics here. This is all unrealistic synthetic data with small numbers, just so it's easy to fit on slides. And I'll step through them one by one. So we start with one full claims history. Now remember what I said, this is actually seeing every single payment at every single date is unrealistic. An actuary would only see summaries per quarter. So let's see what that looks like. So each event date, so accident, notification, payment, finalization, they get binned into the quarter that they occurred in. And then here, for example, we've got payments 3 and 4 both happening in 2022 quarter 4. And the next thing that would happen in this process is we'd just aggregate them. So those two, these two are the ones I was looking at, 2022 quarter 4. That's the 6th quarter, development quarter for this claim. And those two payments, instead of actually seeing that as two payments of $2 and $4, then this process of just summarizing each payment stream by quarter would just add them up. So afterwards, we just see that $6 worth of payments were made in quarter 6. Potentially, there might be another column which keeps track that this came from 2 claims, but not necessarily. That's how the payments would be summarized. The case estimates would not be added up. If there were 2 case estimates within 1 quarter, then the one that was later would be the one that's kept, because that's the most up-to-date one by the end of the quarter. Now, one thing that I've totally skipped up till now is the fact that inflation exists, and fundamentally, this equation here that I've written is actually a lie, because or let's say we'll zoom in on this one. The outstanding for a specific claim at time v, maybe this claim is going to last for another 20 years, for example. Let's say we pay $1,000 every year for the next 20 years. That $1,000 that we pay next year is not equivalent to the $1,000 paid in 20 years' time, right, due to inflation. So we can't really be adding up, say, $20 dollars from 2020 and adding them to dollars from 2050 or something like that. They're just not the same units. We need to put them in the same units before we can do anything. So all these equations I've shown up till now are assuming that you've already done this step. You've already had a separate model which figures out what was inflation in the past, what will be inflation in the future, and accounted for that, removed inflation, put everything to, say, today's money. But if you've got, so this slide is just a diagram. Maybe you would take some kind of wage index to do that, to work backwards, and then also maybe predict it forward and use that to adjust for inflation. Now, I'm not going deep into inflation adjustment today. That's not the topic. It's very difficult, subtle, almost more challenging than the whole reserving task itself in some respect. But what I will point out is that it's so hard because not only is there normal inflation in a sense, there's also claim inflation on top of that, or superimposed inflation, which is the case where if you zoom in on the kinds of payments that we need to make, what insurers need to make, the price of them can go up way faster than say the price of bread and fuel and whatever, all those things that go into normal inflation. So that's to say, there's a hard topic, and I'm not solving it today. Basically, the idea is we need to come up with a sense of the level of all inflation, and figure that out for all the quarters in the past, and then all these monetary values that we did have in nominal amounts, then we look up when they happened. So 2022 quarter 2, that has a some kind of adjustment factor, map it to for each of the claims when they happened, and then multiply it out so that all we're left with everything that has a dollar sign all being the same dollar unit. That's the point of this. Now, once we've done that, actually, we can actually calculate those quantities like the ultimate, like the cumulative paid to date, like the outstanding amount. And so that's what this slide is showing. It's looking, once we've seen a claim, we can all the way until its finalization. We know what we can just add up then. We can look at the cumulative payments, cumulative inflation adjustment payments, and go to the end of the claim. And then what does that value end up at? That's the ultimate. So we know the ultimate, and back at time zero, that number is what is the outstanding amount, because we haven't made any payments yet. And the outstanding liability for each of these different valuation quarters, these different perspectives in time that we focus on the same claim, will be this dropping sequence all the way down to the final, maybe potentially more than one quarter, but at least the final quarter where there's nothing left. Now we've got this kind of situation where everything we know about the claim, say claim K, valuation quarter V, I'm calling that HKV. Some of these are easy to handle bits of data for a machine learning model, but others are a bit more of a pain. So, when did the claim happen? When was it notified? These are just numbers. There's nothing difficult there. But at valuation date V, the sequence of all the payments that have happened up until now, or the sequence of all case estimates that have happened up till now, that's like the number that we have of them is changing with time. And this is kind of a tedious thing for a neural network model. A standard, let's say tabular neural network, they just want, a matrix that comes in, a vector. For one observation, it just wants a fixed vector of length p. It doesn't want that to have more or less columns. It can't handle that really. So our job here for the next section is to take this time varying amount of data. This is history of the claim, and then use some process, which I'm giving this Greek letter phi. I'm sort of blanking. I hope that's a phi, capital Phi. So I'm calling this phi thing just the generic process, which will turn this time varying sequence of information into a fixed length vector. And that's what we'll be doing next. Now, sometimes we have these bits of information, these covariates that are changing with time. And in the simplest case, actually, only the latest value matters. So we don't need to summarize the history up till now. We just take what is the latest value, because that's the most important one. And I'll show you examples later, but many of the other cases, like the payment sequence, for example, the whole series of payments matter. Like we need to summarize the whole sequence. So for example, the payments up until now, we can count how many there were, how many positive payments, how many quarters were there where there were at least some payments made. We could add them up. So that's the cumulative paid to date. That's if we add up all the previous payments, or we can take average, standard deviation, or min max, and all of these summary statistics, that you can do that to any of these other ones, like say the case estimates. You might want to do that too as well. Or maybe not actually the case estimates. That's a bad example. But other ones, so here we're still looking at claim 10 of the different synthetic claims, but we're doing the claim. Now we're looking at the claim snapshotting process, like where if we change the valuation quarter we look at it, from when we know about the claim all the way up until the end when we finish the claim finalized, and we have a whole sequence of different information. So here on the left, let's say here this is, we see the claim developed up until development quarter 4. So some of this information is not changing over time. So the fact that the policyholder, they made the claim and they were living in postcode 1000, well, that's never going to change. So that's always going to be that one. But maybe they didn't have a lawyer representing them at the beginning, at the time of the accident or the first couple of months, but then afterwards they did get a lawyer. They lawyered up, and they've got from quarter 4 onwards, they do have a legal representation. So we summarize that by the most recent value. So for the first couple of quarters, the postcode is the most recent postcode is that, and the most recent legal status is don't know or no. And then from then onwards, we do have they do have a lawyer. So these are the kind of easy ones to deal with. The time series covariates are the ones that are more of a hassle. These are the ones that we need to summarize. So here I'm drawing bar charts to represent the incremental payments made in each of the quarters in the past. So up to development quarter 7, these are we have 1, 2, 3, 4, 5, 6, these 6 past quarters of payments that we need to summarize into a fixed length vector of features. And as I said before, we could maybe take the average, take the maximum, so 10.8 here, maybe the standard deviation, or just add them up. So that's what this cumulative paid to date is here. And as we keep making more snapshots, the summaries would change, right? As we see more data, as we observe new averages, min, max, and so on. So that's how a representation of that changing. And here we've got case estimates. Here it's showing you if you just take the most recent one, because that is in some sense the best most up-to-date guess from the case assessor what the claim is going to look like. But maybe it's worthwhile keeping the history as well. Well, I won't go into that now. Now, once we've got this, this is what, for example, some of our observations might look like after we've done the snapshotting process. So for claim, in the original claim here, we have a sequence of these different valuation quarters, and each of them will turn into a new observation that we can train on. So these are all examples of maybe inputs to a machine learning model, and this is, say, the target, the outstanding value that starts high and then drops down to 0. And I've got a little note here that when it's totally finalized, you wouldn't actually keep this as a training example, because you never want to forecast things that have already happened. So now this is for one claim. One claim could turn into these, whatever this is, 10 different observations, but we still have every different claim, right? And each claim in the portfolio is different, has a different length of history, and it will be going through each claim that we decide to be in the training set, and going through each of the valid valuation quarters and doing this process. Then all of that together would generate, say, the training data set. All of this is the stuff that's specific to all the pre-processing needed for just getting the individual reserving data ready for a standard machine learning model. But the next parts I'll mention are more of a focus on the neural network models in particular. So, of course, here I'm maybe it even occurred, maybe it was a question you were shouting at your screen when you were watching me summarize, the payments up until now by just these crude summary statistics. Oh, not even summary statistics. These crude statistics like mean and standard deviation. Oh, sorry, they are summary statistics. They're not sufficient statistics. So I'm going to be confused. So instead of just taking this potentially quite informative time series and just summarizing them, we could just keep them as time series. Right? We know a method that allows us to do that. That's the recurrent neural network. We could just structure it in a way that for each time claim snapshot, we don't summarize. We don't worry about the fact that the size of the data is, it has a different number of observations depending on the valuation quarter. We just let it be, just throw it into a model that can handle that. And we can do that. I mean, that's exactly, for those ones, you would take, say, LSTM or GRU, pass them into that. The final stage of that process would be kind of a learned summary of that history, and then you could concatenate that with all the other, the non-time series covariates and predict the outstanding. That's perfectly viable. I didn't do that in today's lecture because there's a lot of coding. We didn't do that in the contract work I mentioned, but I have heard of research that does this. And surprisingly, the results it wasn't like this was, night and day better than the tabular method that I'm outlining. It was actually quite mixed. So a lot of work, and from sort of this initial experimentation, not really great performance to justify all that extra work. But that was just one experiment, one data set. As I said, we're making some basic tabular data sets, and as is the case with every one of them we've seen in the course, we need to be doing all that last bit of pre-processing just for the neural networks. Like the fact that the neural networks, they really don't like values to be big or small. They want values that are kind of near 0 and 1. They can't really handle the categorical variables as is. They need to be one hot encoded or something along those lines. So that's the last step here, that even though we've created all these claim snapshots for each of these different claims, then we still need to do this last step. And lastly, I'm adding a couple more tweaks here because of the nature of this data. Reserving data, insurance claim size data, can be extremely heavy-tailed, and that means doing the normal standardization of those kind of monetary values it may not be ideal because of those some heavy outliers in the data could really skew everything. So in that case, for all the monetary values, we can do a log transform. Well, to be specific, it's a log 1 plus x transform, because some of them we are legitimate zeros, and we don't want a zero going into a logarithm. It'll just blow it up. So log 1 plus the value transform is a safe version of that. That sort of removes the heavy-tailedness from potentially causing issues in our model. So this is what we're doing here. We're doing the log 1 plus x before we do the standard normalization of those columns. Okay, so this is one claim. This is all the hoops we have to jump through to get one claim into a bunch of snapshots which are rows of say of a training data set. But how do we even construct a training data set? This is quite a subtle problem. On the one hand, we've got this issue. We know it's a time series problem, so our natural inclination is to split it in time somehow. But how exactly? Then there's a few choices. Here is an illustration of just, say, one whole portfolio over time. we need to take these claims and try to split them into training, validation, and test sets. And remembering that each claim will turn into a bunch of different snapshot rows, but we'll split the data into the training sets in a way that keeps all the snapshots that are generated from, say, claim K all together. So if claim 1 generates 10 snapshots, and we decide that the first one should be in the validation set, then the other 9 snapshots should also be in there together. They should be kept together. And that's to avoid leakage, and also the simple fact that many of these snapshots will be nearly identical to each other. If your claim has gone on for a decade, if you look at the claim after 3 years and then 3 years and 1 quarter, it's probably pretty much the same. There'll be lots of these snapshots where it's very similar. So we want to group them together into the same train, validation, or test set, no matter how we split things. Okay, so I'll outline first the simplest approach to splitting and give you a more complicated alternative later. But we'll start with the simple one, which is we grab all the claims, we find when they were finalized, and then order them by finalization date, and use that, a temporal split on the finalization date, to turn things into train, validation, and test sets. So this diagram is illustrating how this would work. And this is one of these diagrams where each line is a new claim. There's 6 of them. And we've got notification for each of the claims up until finalization for each of the claims. And the idea is that we pick some specific cutoff, so T-train, and every claim that finalized before, up to or including that date, they get thrown into the training set. So these first three claims with the solid line, they're all training claims. Anything that finalizes in between the training cutoff and the validation cutoff will be in a validation set. So here we only get 1 because the one that was notified during the training time but didn't finalize it quickly enough. So it finalized halfway into the between these 2 cutoffs. So we keep it as a validation one. And then the same trick again. So between validation and test, they are the test set. Now, typically the end of the test set would be just the end of the whole data set. Like if we observe up until quarter 2, 2026, then that would be the end of the test set typically. And then anything that still hasn't been finalized by that point, then we legitimately don't know what happens with those claims. So that they are actually what we care about predicting at the end of the day. So we'll call that the unfinalized set, because some of these, don't finalize at specific valuation quarters, but here, I mean, these are the claims that no matter when we view them from, we never see what happens because they just haven't finished yet in reality. Now, one potential sort of subtle issue with this simple splitting procedure is that we may have this bias because they well, let me just zoom in on the diagram to illustrate it that way. Say this is the sequence of claims that we have, and we split them by when they're finalization, before train and before the validation cutoffs. We'd notice that all the long claims survived to land in the test or the validation set. Actually, in this case, this long claim landed in the validation set. This long claim ended in the test set. So our training data is a different kind of data, different distribution of data than the validation and the test, which is really not a good practice. We want the training data to see representative examples that we want to predict in the future. So we could imagine that the training data set gets sort of clobbered with all these short claims that and we don't get a representative sample. So that could be something to worry about. Now, if you had lots of data, maybe this is not even a big problem. But what I'll do later for the synthetic data set, so I'll construct the data set, I'm going to do this kind of burn-in period. Basically, this kind of situation wouldn't happen in a real let's say, depends how you cut things up, but this kind of data set is more representative of an insurance company that just opened its doors and it's just starting to see, from time zero, its first claims coming in the door. Most insurers are not like that. They're in a steady state. Their portfolio has grown, past its original phase of, explosive growth, and it's sort of stabilized in terms of size and risk. And so in that case, what we can do is we can, instead of starting the training data just at time zero, we can pick another date, which is when we're going to start the modeling, and throw away anything that finalizes before that date. And then that way, things that are finalized before that date, that keeps this threshold here equivalent to the other cutoffs, and it will sort of help to mitigate that issue of all the long claims ending in the other sets, because we'll keep some long claims, we'll keep the distributions equivalent between the three data sets. So, I mean, in general, that splitting by finalization quarter is very straightforward, easy to implement, kind of makes sense. Now, I will have a few things to say about the other way, splitting by notification quarter, but I'll point out, students who only are worried about passing the exam for my course, this is not examinable, so I'll just tell you up front, but because it's a bit advanced. So here is another graphic showing the splitting by the finalization date. But what if we instead split by notification date instead? So we take the claims that were notified first, and then groups the first like 60% of them into a training set, the next notified 20% into validation, and the last into test. In a way that's simpler and is closer to what the chain ladder is doing, actually. But the issue is that we suddenly have this case where by the end of certain cutoffs, we don't really see the outcome by that time, and which is not very satisfying. Remember, the whole chain validation testing is meant to be mimicking in real life what you would do. In real life, you would start, collect data, stop, and then all the data you see between those two periods, you can use to train a model, or many models. Then you put them all into production, or into a testing regime, and then you watch them, how they perform for another period, and rank them to be a winner. So that's what the validation set is mimicking. And at that date, you pick a winner, put it into production, and then monitor its performance in reality. And that's what the test set is meant to mimic, that performance. So if we're trying to make train validation tests that are mimicking reality, that's kind of the point, then by the end of the training cutoff, many of these claims here that are in, say, this second blue one, we don't know actually what the ultimate was because it hasn't finalized yet. We only know how much payments have been made up until that point. Now, that's not to say we can't do nothing with that. It's just a little bit more complicated. The claims that, say, up until time, up until a certain time, if we only know the payments that were made up to that point, we say the end of the training data set, this blue claim, we don't know what the size of these payments in the future are, but we do know that at least the ultimate is larger than how much we paid up until now. So we have not a normal observation, we have a ripe censored observation. So we don't see the ultimate, but we see it's at least greater than the cumulative paid to date. And this is the exact kind of survival analysis kind of censoring that we have in that field too. Now, this is the sequence of maybe we'll come back to that in a moment. For the distributional regression I taught you a few weeks ago, I taught you that you start with distributional assumption, turn that into a log likelihood, turn that into a loss function. So if you follow that through, actually, a log likelihood, if you observe all of the targets, would be like there's a product of the likelihood is a product of the densities of these observations of the ultimate values. However, if you have this censored part as well, then you either the likelihood actually changes to this form where you multiply a binary indicator which sort of activates this term if we do have an observation of the ultimate. If we don't have an observation, then the product ignores that term and puts a different term in instead, which is the survival function evaluated at the cutoff. So we know at least that the ultimate is above the threshold. So basically, the likelihood weights those points, those right censored points, by how much probability mass your distributional model puts above the threshold. The payment pays cumulative payments to date. And you can write this is the proper likelihood. You can then do what we did on all those other lectures, turn it into a negative likelihood, turn it into a loss function. And then we can have this data that's split by notification date that has a mixture of claims that really did finalize by the end of the training set, and also incorporate these other claims that don't finalize but are still valuable. They still tell us, the ultimate is at least this big. These censored observations, we can mix them all together. However, and so this diagram is sort of showing you this part here, how much you weighted by if it's if you know that the ultimate is above the payments to date, this dashed line, and you forecasted the ultimate to be this distribution, the green one, the likelihood would sort of reward you by putting more mass in this section here, sort of more mass in the area that agrees with that right censored information that we have. However, remember that at least the way that we decided it before, we made the decision up front that we're not actually going to bother predicting the ultimate. We're going to predict the outstanding, which will, by definition, always satisfy this constraint that it will always predict something that's above the cumulative payments to date. So if you've made that decision earlier on, that outstanding is your target, you're doing this distributional regression, and you want to try to split by notification date, then there's no value. These censored observations are meaningless. They actually don't. This term actually just disappears from the formulas, and so it's all not worth it, basically. Okay, so we can, students who are worried about their exam, you can wake up again, ignore that part. We're splitting the claims by their finalization quarter. All the claims are fully observed within their data set, so we know what the ultimates are. Now let's go on to creating a realistic but synthetic data set and start fitting some models. Okay, I'll be bringing in these two R packages. The first one is to create a synthetic data set. The next one is to do our benchmark chain ladder model. The Python libraries we're relying on are all things that you've seen before in earlier parts of the course. So jumping into the synthetic data generation. So here we just call the generate data function. We tell it kind of the volume of claims we want, roughly 100 claims per period, how many periods, we'll interpret those as quarters. And there's a built-in toggle for complexity of the kinds of data that we have. So it's not the lowest, but it's not the highest number either. Set to see some other part that's not so important. And then we'll get a few different, the sim object here in the R code will have 3 main tables. So I'll show you what these look like. So the first one is a description of each claim individually. So in the synthetic data we've generated, we've created 9,900 individual claims. We get a bit of information about, we see them, so the package generates them in continuous time, so at the highest possible granularity. So we can see, for example, when the accident happened in continuous time, it automatically shows you the per period version too. So this is which quarter it occurred in. A lot of information is duplicated too. So here the ultimate claim size is duplicated. It's shown here for each one, and some of the times between events. So how long did it take for them to notify the insurer? So the notification delay in time, the settlement delay in time. So that's the time between notification and the finalization of the claim. Some high level thing too, like the number of payments over the whole period. The newer versions of this package also generate per claim some static covariates that we could also use as inputs. So does this policyholder have legal representation, categorical for how severe was the injury, and a categorical for the age of the claimant. I don't think I actually use these today, but you could easily feed these in to the models as well. Now onto the main one that we've talked about is the payment stream. This is a much larger data set. So even though we had 9,000 claims in total, this synthetic data set at this highest granularity stores every individual payment, and there's 49,000 in total. So for claim 1, there's 4 individual payments for that claim. So the first 4 rows, payments numbers 1 to 4, they all happened in quarter 1. Some of this information that's static, it gets copied over. It's a little bit of duplication. So, the time of the accident here is the same, is copied many times. Same for the ultimate. Those delays we already talked about. Here it shows the precise time each payment happened. Then converting it to quarters. Now, and then the main one that modelers if we wanted to match the real data, is we should use this payment inflated column. That is sort of nominal values, how much was paid at each of those individual times. But we're not delving deep on the inflation adjustment today. So we'll just use the payment size, which is the version that the package has made without adding inflation. So this is already in the same dollar units. We'll just make our lives easier and use that one. And there's other columns about how much time was there between each payment. The largest table is the estimates table. So this is all the case estimates for these are all synthetic, but for each synthetic claim, all the synthetic case estimates. So the first claim here had 9 different case estimate events. We can see it again copied the ultimate here. This is showing a sort of transaction time, which is it's basically the time when the case estimates were created. So time 2, 3, 5, 7.2, 7.5, 7.7, 8.1, 8.8. That's the time of all the different case estimate updates that were made. And this is just showing the time between the time since the last case estimate update. Here we get the package also simulates a categorical variable, which is to say whether the estimate is a major revision or a minor revision, and some other categories that I won't go into. I don't use this column, but could be of interest. Now, what we'll use is what I've been calling the case estimate in this lecture so far is that what I'm referring to is the case estimator's guess for the outstanding amount for this claim, and that number gets stored in this column. So I'm going to rename this column shortly because I don't like the name of that column. But anyway, that's life. There's a similar version which is called incurred, and you can basically, and we've also got cumulative paid on the claim here. And if you remember from those earlier slides, this is basically that plus that. So we don't need to keep, well, we don't need to keep the cumulative paid for this table. If we just want to keep one set of estimates, we'll keep this one here and throw away this one because that's just a derived from the other one anyway. So as I said, I'll do very minor tweaks to the output that comes from these R packages. I'll lump the static covariates in with the other claim information. I'm going to rename that column, which I don't like the name of, just call it estimate for case estimate. And also throw away that incurred column because it's, as we just looked at, it's just a derived from estimate plus cumulative paid. Most of these, so all the payments, we have a column which we can take the payments which have already had their inflation removed, but the splice doesn't give us a column which is sort of equivalent for the case estimates. They sort of have inflation baked into them. So here, I want to have everything in the same dollar terms, so I'm just manually removing the inflation from the case estimates here, because you can look into the code and see complexity 2 added an inflation of 2% per annum. So I'm just going to rip that out now to get rid of that. And so then everything's just simpler. That's just, as I said, the inflation would be a whole nother topic. Once I've done that, I've saved that and loaded up the data in Python. So I can look at some of the, so for the first claim, what we'll be mainly using, as I said, is the payment size column. For the estimates one, we'll be using, we'll need cumulative paid eventually, but we'll be mainly using the estimate here. And all the pre-processing steps, I went through them in detail earlier, so I'm not going to go through every line of code here, but I'll just at a high level describe what's going on. That is, here we're generating, turning the continuous data into quarterly bucket kind of data, building the snapshots of the claims as well. So originally we just had one single claim, and it went from a notification to finalization quarter of 31 to 61. But after we take a snapshot for every quarter when it was open, then we'll start getting a row for quarter 31, 2, 3, all the way down to 60, but not including the 61. And previously, those quarters where nothing happened, we'll have to generate rows and put in zeros for them for the incremental, because there were no payments. So, but still, we need to represent them as a snapshot with 0 at that time. Well, building the time series of payments, I should say. Now, here is just basically all of those payment history, case estimate history, and then target values themselves, the outstanding. We need to construct them for each claim snapshot at each valuation quarter, and do or add in the summary statistics of the time series elements too. So after going through all the pre-processing that's necessary for the reserving side of things, then we get this style of input, which we can split up and use as training input, for example. So we've got the development period, we've got the incremental that occurred in that period, the sum, the cumulative sum, the latest estimate, and here is the target variable itself, the outstanding amount. Yeah. This is splitting the data by the finalization quarter, what we described, the simple version we described. So we end up with, well, this is not a, the training set is a bit too big relative to the other ones, but anyway, this is just illustrative. End up with 28,000 rows of data, which each row is a snapshot. And these are generated from the 2,790 claims that we keep bundled together as the training set. And you can see all the other sizes as well. Okay, let's fit some models. This slide, I'm basically doing what we've done in the course before, which is standard pre-processing necessary for a neural network. So taking in, for example, the features which were numeric and standardizing them so that they're between 0 and 1, which is what a neural network likes to have. All the variables that were representing dollar amounts, all these monetary figures, I am doing two steps of the processing. I'm doing the log 1 plus x transformation first because they're all heavy-tailed, and I want to sort of make life easy for the neural network and not have all these heavy-tailed inputs. So column transformer will take each of those columns, put them through the log 1 plus x transform, and then min-max scale them. And the categorical, I'm not doing anything special for that, just one-hot encoding them. The target, I will log transform as well. So not log 1 plus x transform, just a straight log transform. So the outstanding in the train validation test, they'll become y train and y bar y test. And for the same reason, the target values themselves are heavy-tailed. In the following, I'm going to fit a GLM which doesn't use the case estimate as an input, and another GLM that does use it as an input, just to see if there's a big difference. So that's why this make preprocessor has an extra line here, which is, do I include the estimate column or not, basically. So we'll make a column transformer, two different column transformers for those two cases. Fit and transform on the training data, and for the validation and test, just do a dot transform. So we get the training, validation, and test. But remember, for this case, we also have a fourth data set, which is all the claims that by the final date in the data set still have never finalized. And these are the ones that the insurance company really wants to make a prediction on. So this unfinalized set. So we've got train, validation, test, and unfinalized without case estimates and with case estimates. Getting the models to fit is actually quite simple once the data's already been set up. I mean, here we've got two GLMs. I'm just doing a basic ridge regression here for the two different GLMs in the first two lines. Here, got a simple neural network feed forward, two hidden layers, one single output layer with no activation. And we'll train it with early stopping and mean squared error loss. So we'll come back to that shortly. We'll come back to it right now, actually. How do we evaluate these models? If we're looking at them claim by claim as an individual reserving model, what kind of we'll look at those predictions. And because we decided to log transform the target variables, our models are all spitting out values which are log dollars. They're not real dollars, they're log dollars. And because we use mean squared error loss, if you think back to the distributional regression lecture I gave, this is basically making the assumption that we think that this thing is normally distributed. The target variable is normally distributed. Therefore, if we try to convert back into real dollars, then we're saying that the outstanding amount has a log normal assumption to it. So I'll talk more about that later, but for the main, in the next slide, but for this slide, the main thing is the targets were log transformed. So therefore, if we start doing, say, root mean squared error on the predictions generated by our models, the units of RMSE are still log dollars. I've made, this is the 4 sets of predictions here. So for the 2 GLMs, the neural network on the test set. Here I'm also pretending that the case estimates themselves are kind of a model and which generates predictions, which is true. It's just not a machine learning model. It's a human learning model. And we use them off screen. I compare it to the true values and calculate RMSE, and we can see that the starting off the RMSE in these log dollars for the case estimates is the worst one, and then we improve on that by using a GLM without case estimates. We improve on that again by using the GLM with case estimates, and again by using the neural network. This is a synthetic data set, so the payment history has most of the information already, and the case estimates are they're random numbers that are simulated to be close to the outstanding. However, I mean, and the result here is that the case estimates are not that, but they are useful, but we can easily beat them too, right? On real data, we might expect that the case estimates themselves alone could be quite a good model, because those people are real experts, human beings making this. That's their whole job, and they probably have data that we don't have access to. Like for the injuries that happen, they probably can see, say, like the medical reports to say this thing is like a spinal injury, or this thing, all those extra details that we haven't been using up till now. So perhaps on a real data set, maybe the case estimates are quite helpful. Just a hypothesis. I've got here a plot of the values that we're trying to predict and some of the predictions. And this is like just a simple scatter plot. And I mean, we want to be on the diagonal. It's not far from it. It's pretty heartening kind of plot for our neural network. But all of these are in log dollars, as I've been saying. We really care about dollars, don't care about log dollars. So how do we get back? I mean, the naive thing to think is that, well, my targets were in dollars. I took logarithms. I took the log operation to turn them into log dollars. So now when my model makes a prediction, I just need to exponentiate it to get it back to dollars again, right? That's a very natural way to think. It turns out to be it's close to correct, but not exactly. Now, the reason is, as I alluded to earlier, mean squared error loss boils down to the assumption that our target, their log outstanding, is normally distributed. Our model gives us the mean, but the variance is a constant variance assumption. That's sort of what we get out of the mean squared error loss function. That means, as I said before, if we transform the target back into a distribution for the outstanding, that thing is log normal. Log normal with mean mu k and sigma squared k. And the mean of a log normal distribution is actually this. It is the exponential of the underlying mu plus half of the underlying sigma squared. Here is it visually. A log normal distribution, here drawn in green. If you just take the exponential of the mu, then you get a number. That's this orange curve. That's too small. Basically, if you compare that to the actual mean of this distribution, it's this pinky kind of dotted line to the right once we've added in the half sigma squared. So if we just did the naive thing, we just did a naive exponentiation of the predictions from our models, we would systematically under reserve with our models. So to get to when we make predictions, I've got this little function here that will convert them from log dollars back into dollars. It's basically the formula for the mean of a log normal distribution. So I put in our predictions there, the sigma squared, and these 4 lines are just estimating the sigma squared that's implied by the different models. Now we've got things back. We know how to convert back to dollars. So we could go back and do, say, RMSE again, but instead of the log dollars, calculate it in dollars. That's totally fine. That's not super interesting though. So I wanted to show you something that's more specific to the individual reserving, which is comparing our predictions against the case estimates directly, head to head. Now, this beta percentage is a metric that either Greg Taylor or one of his students came up with. I don't know the exact history of it, but it's basically we take a set of claims, say the test set, and we make predictions on them, compare them to the case estimates, and compare both of them to the true values. And then we go through and say, what fraction of the time were we closer to the true value than the case estimates? So there's a bit of code, shows it here. We can look at the percentages afterwards, and we get a better percentage of mid-30s for the GLMs and close to 39 for the neural network. Maybe this doesn't look very promising though. I mean, of course we would like to be about 50%. That means that more often than not, we're beating the case estimates. But we must remember that actually the way I described it just then, if we just put in all the claims and then see the fraction of the time that you're closer, we are giving equal weight to the claims, these little tiny claims that are only a little bit of money, and we're giving them as equal weight as we do to the massive claims that really cause a lot of trouble. So in a sense, winning the claim that's worth $2 million getting close to that should be more important than getting like very close to this, like a $5,000 claim. So this is what the weighted beta percentage does. It's another metric that this team came up with. Basically, you grab the claims, see how big they were, their ultimates were relative to the others, and use that to weight up and down each individual competition, if you like, and then this gives you a sense of when it counts, which models are the other models better than the case estimates for these big claims where it's really important to be right, and our models look better after we apply that. Basically, the models GLMs, even the GLMs are a little bit above 50%, and the neural networks are 56%. So, and remember, none of these models I'm showing are hyperparameter tuned, so I'm sure you could do better than this. From one sense, the predicting every individual claim accurately is kind of interesting and useful for some applications. A lot of the time, though, for a lot of the actuaries world, they actually care about the portfolio total more. And so now the benchmark in that world is to compare our model against the chain ladder model. So here I've gone back to R, taken out payments window, and turned it into a triangle. So this is a cumulative triangle. This is saying that for the accident, and it's done by year. So accident year 1, development year 1, there was 0.3 of $1 million paid out in the portfolio. So not much. By the end of accident year 2, there had been cumulatively $3 million paid out for this, and then 3 to 9, all the way up to, and then by the end we sort of stabilized it by around $70 million for this year's worth of accidents. And we can take this, do the trick where we fill in based on the ratios above, or variations of that core idea, and fill in the triangle basically here. So I'm not going to do that by hand. The chain ladder method package, has some functionality. I'll just use it directly. and it comes up with the number for the whole portfolio. Chain ladder, well, the MAC chain ladder is saying we need to keep $275 million aside for these future payments. We don't get a immediate way to compare our individual models to the chain ladder because one's at the single claim, one's at the portfolio, but so we have to add up. And the basic way to do it is to basically come up with a prediction for each claim at the end of the at the equivalent valuation date to the chain ladder. What's our prediction for the outstanding for each of those claims that are still open? Add them up, and that will be an estimate for the total reserve. And that's what I've got here. A bit of code to do that for each of the models. And now we've got estimates that are almost comparable. The estimate for the portfolio reserve, how much is left to be paid. And now I'll start with the chain ladder one. Let's see, it's perhaps the simplest one. Here we have a number where I said before it's about 275 million, and the chain ladder is trying to get to this dashed black line. I mean, normally you don't know the true value, of course, but this is all synthetic data, so we can sort of see what happened in the future and figure out what it should be, what the true values were for these things. So the chain ladder is a little bit underneath. It's missing its target, under reserving by 25 million or so. But it's pretty close overall. Now, all these individual models, they are actually trying to actually get to this pink line. Now, that is because that's the true value if you look at all the claims. So we're doing T of V here. If you look at all the claims that had been notified by this valuation date V, and then you see how much was outstanding for each of them, add it all up, and you can see the true value for that, then that number is what all these individual models are trying to get to. And the GLM overshoots it. The first GLM overshoots it by a lot. The case estimates gets us a bit lower, and the neural network gets us a bit closer again. But it's sort of overshooting it. It's 290 million or so when it should be about 260. Now the difference, remember, between these two here, what the individual models can do if you just add up their predictions together, that's fundamentally less than what the aggregate models are trying to estimate, because they will capture this incurred but not reported claims that the individual models just can't. Well, we have to manually do something afterwards to estimate that, which I'm not doing here. So overall, the models are aggregate and individual. I don't have a lot to say here comparing them, because again, next week's lecture that's one of the main topics. But we can come to some high level conclusions straight away. The aggregate models certainly simpler, way simpler, stable, industry standard. We throw away lots of data, and we can't really get an idea of per claim what we should be expecting. The individual ones, we do get that low-level predictions that may be useful for tasks that aren't reserving exactly, but related tasks. But we miss it. We can only get to T of E, which is not including the IBNR. And admittedly, this is something I felt very keenly in the recent years, that when you do this individual level reserving, the data engineering is a lot of work. You're really keeping track of lots of little things. It's a long sequence of pre-processing, and getting any little step wrong, the whole thing falls apart. So it is there's a lot to promise, but you have to work for it. You really do have to work for it. As I said, IBNR, you need something else. I didn't add here, but really the inflation, doing that correctly, that's a whole thing on its own. Uncertainty, that's like what key ones. So here we just came up with a single number for the whole portfolio, but really we probably more useful to have a distribution over the portfolio reserve, which we can do if we aggregate it, if we do it in a distributional sense and aggregate the distributions, but I just don't have time to go through that. And I mean, the general question, again, I'm leaving to next week. When should you really beat? When should you really pick one or the other? Leaving that for the experts to explain. Okay, finishing up the packages for Python. The different versions are all here. I'm sure there's lots more references. I just only including here for the ones for the R packages that we spent a lot of time on for the synthetic generation. Although I'll update this slide for the website too. I really should put the reference for the chain ladder. Now I think about it, at least. But yeah, that's the topic for today. I hope that you enjoyed it, that you learned a lot, and I hope to see you, if you're some of my students, I hope to see you next week for the guest lecture in person. I'm very looking forward to it. See you then.